Welcome back, everyone. Just give me 30 more seconds. People are still joining, and then we shall start. Right. So let's start with our next topic. What we have started with, we started discussing all the celestial bodies. We discussed about the stars, black holes, and then the sun. Now we come to planets. Now, when it comes to planets, first and foremost, again, try to understand how do we classify something as a planet, and then after that, we shall go into the details of it. So, first and foremost, when we say that something is to be called as a planet, there are certain criteria that have to be fulfilled if any celestial body has to be called as a planet. Now, what we say is that first of all, a planet is any astronomical body orbiting around a star which is massive enough to be spherical due to its own gravity. Something that we discussed about the stars as well, that they have to be massive enough that they are held by their own gravity. They get their stability of the shape because of the spherical shape. Spherical shape is supposed to be the most most stable of all the shapes that we have. Right. So that's the first criteria. Second is that they should not be massive enough to cause thermonuclear fusion. So this is where they are different from the stars, right? In the stars, they have to be big enough that thermonuclear fusion can happen, and they have to be bound by the spherical shape because of gravitational force. So we know about these two things when it comes to a star, and this is where a planet is different when it comes to the second criteria, that there is no thermonuclear fusion reaction that happens inside the planet. Now, for a very long time, these were the only two criteria uh, for something to be called as a planet. All right, these were the two criteria that were to be fulfilled, and if these two criteria are fulfilled, you will say that okay, fine, this is a planet. Now, then there was a complication, and you might know today that right now we say that there are 8 planets in the solar system. There was a time when we used to say that there are 9 planets in the solar system, and this is where we stopped calling Pluto as a planet, and Pluto was reclassified as a dwarf planet. Correct? Pluto is something that we now call as a dwarf planet, although we used to call it as a planet. Correct? So this change happened because of the third criteria. This change happened because of the third criteria, and this third criteria was added later. This was 2006 when the third criteria was added. Now, why this third criteria was added is because there are other planets also, or there are other celestial bodies also, which are revolving around the sun, which have a spherical shape, and thermonuclear reactions are not happening. So there were new discoveries happening all the time. For example, especially in this case, there was a discovery of a planet called as Aries, or a celestial body. Let's call it as a celestial body, a celestial body called as Aries. Now, as soon as this Aries was discovered, the discovery of Aries, what we saw was that first of all, Aries also spherical, just like any other planet. Aries also revolves around the sun, just like any other planet. And the size of Aries was seen to be bigger than Pluto. So, bigger than Pluto, spherical, orbits around the sun. Why not call it as a planet? It should be called as a new planet. But then what the scientists thought is no, let the list of planets be an elite club, that no other new entrant should be there in this planet. So this is where they started thinking of the third criteria, and the third criteria was thus added, that a planet should have cleared its neighboring region of planetesimals, meaning that there should not be anything in the surrounding. So, for example, the path that any planet is following, it should not have anything in that path. Everything should be clear. Even if there is something in the surrounding, it should be revolving around that planet. Just example for, let's say, if you say the Earth. Earth has the moon, right? Moon is the satellite of our Earth. So even if moon is in the surrounding areas of our planet, it is revolving around the planet. It does not have its own independent path. In case of Pluto and Aries, Aries has its own independent path, is close to Pluto, and is not affected by Pluto. And then we saw that the size of Aries is bigger than Pluto. So why wouldn't you call Aries as a planet, right? So sorry. So this is where we see that the things changed, right? This is where the things changed, that anything that is a small celestial body, planetesimal, meaning anything which is like a planet or which is like a small celestial body, uh, it should not be present in the path of this planet's orbit. So this is where we see that the things changed, and Pluto was reclassified as a dwarf planet because of Aries, because of the discoveries that were associated with Aries. Now later on, what we found is that size of Aries is actually smaller than Pluto. There is this New Horizons mission that was launched and which went near Pluto and Aries and all this region around 2015. And there it was found that Aries is actually smaller than Pluto, meaning that all our assumptions were wrong, that Pluto lost its planethood for nothing. It was a wrong observation, a wrong calculation, because of which Pluto had to suffer. And it is still suffering, right? It is still suffering. There are still people fighting on Instagram for justice, that there are hashtags justice for Pluto and all that, just to show their support for Pluto. But unfortunately, Pluto has been reclassified as a dwarf planet. When do we call something as a dwarf planet? Something will be called as a dwarf planet when the first two criteria are fulfilled. First two criteria are fulfilled, and then the third criterion not fulfilled, then in that case it will be called as a dwarf planet. So that's why Pluto is a dwarf planet, Aries is a dwarf planet. There is another one called as Ceres, which is also classified as a dwarf planet. We have Ceres. So all these are dwarf planets. So planet when all the three conditions are being met, dwarf planet when the first two conditions are met but the third condition is not met, then in that case it will be called as a dwarf planet. So with regards to, so that's why planets, just remember this part, it becomes very crucial from the perspective of your exam, just to understand the basic difference between what is a planet and what is a dwarf planet. Then after that we have another celestial body called as a comet. Now when it comes to comets, just understand, now there again there are three different celestial bodies that we are going to discuss here. One is a comet, then after that you have an asteroid, and then there is a meteoroid. All right. So comets, asteroids, and meteoroids. So just again try to understand the basic differences between these three celestial bodies. First and foremost, we have a comet. Now, in case of a comet, what we say is that comets are cosmic snowballs of frozen gases, rocks, dust, which are roughly of the size of a small town, meaning that almost 5 to 10 kilometers in radius is what you will have. So let's say even if you consider 5 kilometers radius, it is good enough size. So in a comet, what we see is that comet might have dust, ice, carbon dioxide, ammonia, methane, etc. All these things. Plus, it would have metals or maybe other minerals or rocks can be also be present. Minerals or rocks, etc., can also be present. So basically the core, the center will be made of all these metals and minerals, etc., and then all the dust particles and the ionized gases, carbon dioxide, methane, ammonia, etc., all these will be also there. So this is how we see that a comet will be uh, seen. And now in case of a comet, most prominent feature of a comet is the tail that the comet shows, right? Something like this, that there will be a kind of a center or a head, and then there is a long tail. Now this tail basically is produced because of the motion, because of the motion of the of the comet. Because comets, remember this, that comets also have a fixed path around the sun. All right, they have a much bigger orbit, although, but they have a fixed path around the sun, and they also keep on revolving around the sun. They have a fixed orbit around the sun, 5 to 10 kilometers in radius, 5 to 10 kilometers in radius. And one more thing, although made of metals, minerals, all these dust and gas particles, etc. At the same time, at the same time, comets also have an atmosphere. Comets also have an atmosphere. So that also, so this also becomes a very, very crucial aspect of what comets are. So comets have an atmosphere 5 to 10 kilometers in radius, made of metals, minerals, carbon dioxide, ammonia, methane, etc., and then revolving around the sun in a fixed path. Most of the comets are found beyond Neptune. Most of the comets are beyond Neptune, but they have a fixed path around the sun. Now, after comets, we have asteroids. Now, just try to understand how asteroids are different from comets. First and foremost, they are small. All right, they are small. When we say small, most of the asteroids they would have a diameter of 200 meters, 300 meters, maybe if they are very big, 600 meters, 800 meters. That's it. So, at one hand, we are talking about 5 to 10 kilometers in radius. On the other hand, we are saying 200, 400, 500 meters. That's it. Half a kilometer maximum. So very small compared to a comet, very small. So when we say small, generally we see that it is in the range of 200 to let's say 500 meters. Many of them will be even lesser than that. I mean, they can be even 50 meters, 70 meters in their radius, and they can be up to 700, 800 meters in their radius. So much smaller as compared to comets. Then they are airless. Airless meaning no atmosphere. No atmosphere, correct? So in this scenario we see that it's again different from a comet. Then also when it comes to an asteroid, mainly what we see is that asteroid could be made of anything that can be found in the composition of any planet. So for example, let's say when you consider any planet, you'll see that planets consist when you see any planet, you'll see that planets consist of metals in their core, or carbon is present in their core. Many different minerals are present in their own. So similarly, we see that even asteroids are similar. That there will be some asteroids which are metallic asteroids. There are some asteroids which will be carbon-rich asteroids. So it depends because they are very small in size, and also believed that most of the asteroids that we have in our solar system, the formation might have happened at the early stages of formation of the solar system. You might know that there is an asteroid belt. Have you heard of it? There is an asteroid belt between Mars and Jupiter. So, what is believed is that between Mars and Jupiter, there might have been a planet in the early part, but because of the gravitational pull and other activities from Mars and Jupiter, this planet between Mars and Jupiter could not sustain, and it just broke off into various different pieces. It just broke off into many pieces. So, as it got broken into many pieces, this is where it basically formed an asteroid belt between Mars and Jupiter. So that's why they have a composition very similar to the composition of a planet. That they have metals, they have carbon, etc. So that is what we see with regards to an asteroid. Now, the third concept is of a meteoroid. So now again understand what is a meteoroid. Size wise, much smaller in size, much more smaller in size, just around 10 meters. Dust particles just around 10 meters, 20 meters, that's it. So very, very small. So comets are the biggest, followed by asteroids, followed by meteoroids. Now these meteoroids, so about comets we discussed that they have a fixed path, most of them beyond Neptune, but they have a fixed path. Asteroids also, most of them they have a fixed path, most of them are in the asteroid belt, again revolving around the sun. But there is nothing like that with meteoroids. They don't have a fixed path. They would be just freely hanging around in the solar system and have no fixed real path. Now these meteoroids, again, they can be made of iron, they can be made of nickel, they can be made of various different minerals, very small pieces. Sometimes what can happen is that, let's say, this meteoroid, while just hanging around in the solar system, might come very close to the earth. all right, might come very close to the earth. And as soon as it comes close to the earth, of course the earth's gravitational field starts to take its effect, and this gravitational field will pull the meteoroid towards itself. All right, the meteoroid will be pulled towards the earth, and then it starts to fall on the earth. Most of these meteoroids that fall, they would completely burn up in the earth's atmosphere because of the air resistance that the that the atmosphere presents to this meteoroid. So then it will completely burn up. Those kind of meteoroids that completely burn up, they are called as meteor. But then there are chances that it does not burn up completely and a small fragment falls on the surface of the earth. Then in that case, it will be called as a meteorite. All right. So just understand the basic difference between the three terms. They're not different in their composition. The difference is only in the way where they are present. So if they are present, let's say somewhere in the universe, somewhere in the space, they'll be called as a meteoroid. As soon as they start falling on the surface of the earth, they are called as a meteor. And if let's say they are able to sustain the friction of the earth's atmosphere, and one small particle falls on the surface of the earth, then in that case it will be called as a meteorite. So that's the basic difference between the three terms. So so meteoroids, they are made of mainly iron and nickel. Then meteoroid that completely burns up as it passes through the earth's atmosphere is called as a meteor. And a meteoroid that survives the falling is called as a meteorite. All right, so that's the basic difference between these three terms. So just understand that how exactly do we define these terms. All right, now from the perspective of when we look at the examination, what we also see is that sometimes when it comes to all these terms, they have been asking questions from here. For example, let's say when we talk about the meteoroids, you might have heard about the dinosaurs, that dinosaurs once used to reign the earth, and then all of a sudden what happened, that there was a meteorite shower that happened on the earth. A lot of meteorite pieces fell on the earth, and because of that dinosaurs lost their lives. Many a times it is also believed that if you make a wish looking at a falling star, a shooting star as you call it, so meteors basically are called as shooting stars. They're also called as shooting stars. So people go and make a wish when they look at this shooting star, right? Same would have happened with the dinosaurs. That the dinosaurs might also have made a wish, and their wish came through. So what happened at the time of the in the when we look at the Earth, Earth's geological history, what we see is that in case of meteorites, when the meteorites fell on the earth, the impact would have been enormous. All right, impact would have been enormous, because of which a lot of dust particles also might have been raised from the earth because of the impact of the meteorites. Because of that, what happened is that a kind of a cloud of dust was formed all across the earth. Now what happens is that these kind of clouds, they completely block the sun's rays. Sun rays are blocked, no photosynthesis happening here, plants die out, all the animals dependent on them die out, all the carnivores dependent on the other animals, they die out. So ultimately what we see is that because of this one event, almost 85% of all the life forms that we had, almost 85% of all the life forms that we had, everything was lost. Almost 85% of it was lost. So unfortunately this is what happened, and it led to a mass extinction, something which is called as a mass extinction. So overall this happened. Look at this question. This question was asked in your 2012 paper. Read the question and then I will launch the poll for you. Right. So 3% of you have marked A, 60% of you have marked B, 17% C, and 20% of you have marked D. So let me discuss this with you. Most of you are, of course, correct. What is the difference between asteroids and comets? First is asteroids are small rocky planetoids. This is correct. While comets are formed of frozen gases held together by rocky and metallic mineral material. We discussed this, that rocks are present, metals are present, ionized gases, frozen gases, all these things are present. Carbon dioxide, ammonia, methane, all these things. So this is correct. Asteroids are found mostly between the orbits of Jupiter and Mars. This is perfectly correct. While comets are found between Mercury and Venus. No, what did I tell you? Beyond Neptune, right? Most of it is found beyond Neptune. Two is completely wrong. Comets show a perceptible glowing tail while asteroids do not. This is correct. Comets are known for their tails, right? And asteroids don't have any such tail that they show. So correct answer will be 1 and 3 only. Moving on, the next topic is Kuiper belt. Now, Kuiper belt in very simple terms, let me just show you through this diagram that what exactly Kuiper belt is. So, this Kuiper belt basically is a region beyond Neptune where you have a lot of small celestial bodies. A lot of comets are found here, a lot of meteoroids are found here, small rocks, dust particles, etc. They just are found here. A lot of dwarf planets are found here. All these things are found in the Kuiper belt. Now, why in the Kuiper belt they are all formed? Because by the time you are in the Kuiper belt, you have come very far away from the sun. Correct? You have come far away from the sun. So the gravitational pull of the sun is now weak because of the distance. It is now weak. And because it is weak, it's easy for you to exist as a small celestial body as compared to if the same celestial body was in the inner atmosphere, in the inner solar system. It was near the sun, it would have been pulled by the sun. But because it is so far, all these smaller celestial bodies, they can very easily exist here. So that is why we see that a lot of all these particles, they are found here. So disk-shaped region beyond Neptune extends between 30 to 55 astronomical units. Can you tell me how much is one astronomical unit? Anyone who knows quickly? How much is one astronomical unit? Yeah. So one astronomical unit is basically the distance between the sun and the earth, which is approximately 150 million kilometers. All right. So distance between the sun and the earth, which is almost approximately 150 million kilometers. Distance, I'm just writing it out here. Distance between the sun and the earth. So this is what we see with Kuiper belt, that it has 30 to 55 astronomical units, meaning 30 times this distance between the sun and the earth. Now, what we see is that most of the smaller celestial bodies are found here. So, for example, as I told you, the dwarf planets, most of them are found here. Dwarf planets, except Ceres. Ceres is the only dwarf planet which is found in the asteroid belt. Dwarf planets except Ceres, then all most of the comets, many meteoroids, dust particles, etc. All these are found in this particular Kuiper belt. Even Pluto, for example, Pluto is also found in the Kuiper belt. So in this manner, we see that this becomes a region where all these smaller celestial bodies can exist. Then after this, lastly, we have something called as the Oort cloud. Now, Oort cloud, when it comes to the Oort cloud is, you can say, the end of the solar system. In a manner, you can say that it is the end of the solar system because, first of all, it starts between 2000 and can go up to 2 lakh astronomical units and consists of various ices such as water, methane, ethane, carbon monoxide, hydrogen cyanide. All these things can be present here. So, in a manner, we see something like this, that the solar system has ended, the Kuiper belt has ended, Then after that, there is an interstellar space, and ultimately the Oort cloud. So Oort cloud, in a manner, you can say it's the boundary between two solar systems. That one solar system has ended, the second has not begun yet. Between that, the no man's land that we have, it is called as the Kuiper. Sorry, it is called as the Oort cloud. So after Root Cloud, again we'll have another solar system outside. For example, Alpha Centauri is the closest of all the others that we see, the other solar systems that we have. So it will start beginning there, and it will also have its own planet systems, which will be also called as exoplanets. Exoplanets basically are the planets outside our solar system. Exoplanets are the planets outside the solar system. So they basically will be found beyond the Oort cloud. This is a question. This was asked in your 2015 paper. The term Goldilocks zone is often seen in the news in the context of. So I'm not launching a poll because we have not discussed what Goldilocks zone is. So Goldilocks zone basically is the habitable zone. It is the habitable zone around any planet, around a star, with moderate temperatures. Moderate temperature that can sustain life. All right. So this is basically what Goldilocks zone is. That we are. So that's why if you look at the four options that have been given, the most appropriate answer could be C. Search for Earth-like planets in the outer space, because we are trying to find areas where there are the temperature is moderate, and that's why life forms can exist there. So that's why chances of finding life in such an area can be higher. So this question was more or less a current affairs question asked in the context of a mission that was launched called as the Kepler mission. So Kepler mission was a mission which was basically carried out to find these kind of planets or these kind of areas where chances of finding life is there. And if we have any planet which lies in the Goldilocks zone, then there are higher chances that that planet can sustain life. So that is why Goldilocks zone, and this is the question actually that was asked in your paper. All right. So if you have any questions with regards to whatever we have discussed here in the last half an hour or so, please let me know. And then after that, we shall begin with the next session or the next topic that we have. But before that, if you have any doubts, please let me know. Oot can't understand. So cloud, basically what we are talking about. Let me go back to the Oot cloud. So Oot cloud, what we are saying is that, see, this is where the solar system has ended after Neptune, and this is where the new solar system begins. Between that, you have this area which is called as the Oort cloud, and this Oort cloud is an area which might have a lot of icy objects. As you can see here, a lot of icy objects could be present, and all these basically they form a boundary, a huge space between this solar system and the next solar system is formed. So that's why 2000 to up to 2 lakh astronomical units. Just imagine that the distance between the sun and the earth is 1 astronomical unit. Here we are talking about up to 2 lakh astronomical units. So you almost have gone beyond the reaches of the sun. The gravitational pull of the sun, the of the sun can't really reach these areas. So that is the Oort cloud. Does exoplanet revolve around the sun? No, no, no. That's why exoplanets, because these are outside the solar system. They would have their own star, they would have their own sun, and they would revolve around their own sun, not our sun. All right. That's why exoplanets, because these are outside our solar system. Vibranium. Yeah, vibranium is a hypothetical example of meteoroid. Correct. How are the tails of the comets formed? So, tail of the comet basically is formed because of the motion. Just understand what's happening. That what happens is while the comet is revolving around the sun, when it comes closer to the sun, then in that case, all the frozen gases that the comets have, they start melting. And once they start melting, they actually form the cloud of dust, which is actually visible as a tail. Why it can't be recrystaled to the planet? Unfortunately, I mean, it's not that it can't be. There have been a lot of discussions also that have happened around around this problem, that Pluto should be reinstated as a planet. It may so happen in the future. Until now it has not happened, and I mean, I vehemently support that something like this should happen. You can't make others suffer for your mistakes. So this was the mistake of the scientists, a calculation mistake that led to this kind of a situation. Please explain asteroids once. So asteroids, two, three important points. Just remember this. One, asteroid formation might have happened in the early solar system when there might have been a planet between Mars and Jupiter, which just broke off into many pieces because of the gravitational field exerted from both the sides, from Mars and Jupiter. Might be because of that, broke off into pieces, still revolving around the sun in that asteroid belt. Very small in size, 200 meters to 500, 700 meters, that's it. Could be made of metals, could be made of carbon, could be made of anything that a typical planet is made of, because it is believed that it might have been broken off pieces of the planet. So just remember, and does not have any atmosphere as such, so that's why we are saying that it is airless. Planet system is mysterious. Yes, of course. I mean, there are a lot of things going around there which we can't understand yet. That's true. All right. So let's move on to our next topic, which is space technology. So until now, what we have discussed is basically the science of space. Until now, we have discussed the science of space. Now we'll move on to the technology. Now, when it comes to space technology, we are going to discuss here about what are satellites, how we launch satellites, understanding the basics behind the launches, and then all the things that India is doing and all the things in the perspective of India. So these are the things that we are going to discuss in this second part. So to begin with, first and foremost, we need to understand how the observations are made. So observations can be ground-based observations and space-based observations. So when we say that it is ground based observation, the meaning of the ground based observation is that you are sitting on the ground and you are making all the observations. All right, you're sitting on the ground and making the observations, meaning using the telescopes. What do we do with the telescopes? You sit at your home and you look at the night sky trying to observe the solar system, or maybe even small bodies outside. So then in that case, what happens is that these are ground based observations. So ground based observations basically meaning using the telescopes. Now, in the telescopes also, there are a lot of different types of telescopes. Although not all the telescopes are important for us, there are two telescopes which are very important. One, the optical telescope, and then the second one called as the radio telescope. So we'll try to understand what we mean by optical and what we mean by radio telescope. Now, optical telescope is the kind of telescope that captures the visible part of the electromagnetic spectrum, meaning that it sees the world in a very similar fashion as our eyes see the world. So, what we can also see, what we see around us, is also the visible light. Correct? We are able to see because of the visible light. And similarly, an optical telescope also takes all its observations in the visible light. So that's why it is called as optical. Anything that uses visible light is called as optical. So that's why optical telescopes are the most commonly used and the most popular types of the telescopes. So captures the visible part of the electromagnetic spectrum. Now, when it comes to the optical telescopes of India, there are three major optical telescopes that India has. One is in Devsthal in Uttarakhand, one is in Hanle in Ladakh, and then there is one in the Javri Hills of Tamil Nadu. So these are the three most prominent of the optical telescopes that India has. Now, when we look at all these telescopes, especially the one that we have at Hanle is a very, very important telescope. You might have also come across the news, which was very often discussed last year, something called as Dark Sky Reserve. Heard of it? It was in the news last year, Dark Sky Reserve. So now, Dark Sky Reserve, just understand what Sky Reserve is. This is an area, and I'm specifically talking about Hanle in this scenario. Hanle is an area which is a very secluded area, very far off from any kind of settlement, any kind of population. Located in Ladakh, first of all. Ladakh, anyway, is very sparsely populated because it's a cold desert, not easy conditions to live in. So, even Leh city has a very small population. If you go beyond Leh city, the entire Ladakh area is almost vacant. So, very secluded, far off area. Hanle is almost near China border. So that also creates a complication that it's not easy to go there. You need permissions to visit the place. There's no electricity there. They completely rely on solar energy. There's hardly any rainfall. In the entire year, what we see is that there are more than 300 days of cloudless skies. More than 300 days of cloudless skies. So just imagine there is no rainfall in the entire year, maybe 1 or 2 days of rainfall, that's it. So sky is completely clear, away from any kind of population, away from any kind of settlement, away from any kind of air pollution or land pollution, because Hanle is very far off. So even, for example, let's say if you have to visit Hanle, I mean, I'm just giving you a tourist information, that if you have to visit Hanle, there's only one bus in every week that goes from Leh to Hanle. Every Saturday, I believe that there is a bus that leaves from late for Hanle, and then every Sunday it comes back. So you can only go on the Saturday, and maybe if you want to stay there, then 1 month, 1 week later, you can come back. Otherwise, you can't. So very far. That's why I'm saying that it's a very far off area, and also the temperatures are also very harsh. The summer temperatures are still moderate. The summer temperatures are -5, -6 degrees Celsius. Winter temperatures can be -20, -25 degrees Celsius or beyond that. So that's why very harsh conditions, no water, no electricity, hence no tourist. So it's a wonderful place to visit actually. So, and that's why it was also an area chosen for making the dark sky reserve. So what is the meaning of dark sky reserve? Dark sky reserve is where you would go just to stargaze, just to look at the night sky and feel wonderful about it, that there are so many, you can't even imagine how many, what the scenario from there is. I actually went to this picture that you see here. I actually had clicked this picture. It's not a picture taken from Google, and I went there in the month of December. So this bright sunlight that you see in this picture, this bright sunlight is of -20 degrees Celsius almost. So freezing temperatures, chilling temperatures, and but the views. I mean, the night views are exceptional. You can't even imagine if you've not been to such a place, maybe somewhere other place in the country as well. You can't even imagine the kind of scenario that you have there. And that's why, I mean, for me it was a must visit place. I went inside this telescope as well. They showed me around how exactly they do everything, but you can't, I mean, you need permission from ISRO if you want to go inside and make the observations, otherwise it is not allowed. So this part that you see, this part will basically open up and the observations will be made from here. So this is how basically this optical telescope works, and hardly, I mean, from that perspective is a wonderful place. So let's move beyond tourism to radio telescopes. So now, in case of a radio telescope, what we see is that radio telescopes basically will capture the radio waves. All right, the invisible radio waves will be captured by the radio telescopes. Now, in this scenario, what we see with radio telescopes is that Be capturing radio waves. Now we can't see radio waves, we can't comprehend radio waves, our eyes cannot. For example, your mobile phones, they run on radio waves, but do you see radio waves? You don't. Otherwise you'll just see floating waves all around, right? But we can't really see them. So radio waves are being captured by the radio telescopes, and that's why they will be, the kinds of images that also that they take is very different from the images that you will observe with an optical telescope. Two important radio telescopes that we have is one in Pune in Maharashtra, and the other one is in Uti in Tamil Nadu. So these are two radio telescopes that we have. So that's why. Just look at these two pictures. The first picture, this has been taken by an optical telescope, and the second picture that you see here, this has been taken by a radio telescope. So do you see the difference? The first picture that you see is very similar to how we would observe if we were looking at the same celestial body, and the second picture has a very different view. This is not how we see the world. This is not how our eyes comprehend the world, right? So that's why there's a lot of difference between these two. They basically, one captures all the visible part of the electromagnetic spectrum, and the other one captures all the radio waves coming out of these planets or any celestial body for that matter. Now, so this is how we look at radio and optical telescopes. Now coming to the space based observation. So until now what we have discussed is that we have ground based observations which are based on telescopes. Now we come to how the satellites are launched and how the satellites are kept in their orbit. Now, to launch any satellite, there are few small important concepts of physics that are applied in launching any satellite. I am trying to just oversimplify what actually goes behind the scenes. Otherwise, it's a very complex technology altogether. But there are some simple rules that are followed. So, for example, an object in motion will stay in motion unless something pushes or pulls on it. This is what? This is an explanation of Newton's first law. Newton's first law of motion. What does Newton's first law of motion say? It says that an object at rest will remain at rest, an object in a uniform motion will remain in uniform motion unless acted upon by an external force, right? Something of what you see in this picture, that you will remain at rest unless an external force is applied on you when you are studying, when you are supposed to study. So then in that case what we need to understand is uh, how exactly do we make this happen. So try to understand this from this particular picture. What we are saying is that there should be a balance of forces for anything to remain at its place. Now if we are launching a satellite, all right, when we are launching a satellite, let's say, has to go to, suppose, 1000 kilometers above the surface of the earth. So at 1000 kilometers above the surface, the forces that are applicable on this satellite, they should all be balanced, right? They should be all balanced. How will we do that? There is one natural force, which is the force of gravitation, which will keep pulling this satellite towards the earth, correct? So we have to provide another force which is in the opposite direction of this gravitation, correct? Opposite direction, so that you can balance out these two forces. So there is one force which is because of gravitational force, and there is one force that you would apply, correct? So these two forces have to be balanced, and if these two forces are balanced, wherever they are balanced, that is where you will see that the object will remain in its orbit. So for example, let's say if I have to place a satellite at 1000 kilometers above the earth, then I have to do calculations in a manner that at 1000 kilometers above the surface of the earth, all the forces acting on that satellite, they are all balanced, and hence the satellite can remain in the orbit at 1000 kilometers. If I have to do the same at 10,000 kilometers, I can do the same. The calculations will change, but the basic concept will remain the same, that forces have to be balanced. Wherever you have been able to balance the forces, you will be able to make the orbit remain there. So now, when in this case, so that's why, just remember that we have to balance the forces. Balance the forces. One force is centripetal force, which has to be equal to the centrifugal force. Centripetal force has to be equal to the centrifugal force. Centripetal force basically here is the force due to gravitation. Centripetal force is the force due to gravitation, and centrifugal force is the force due to motion. So centripetal is what? Something that acts towards the center, right? So this is what gravitation is doing, that acts towards the center. And centrifugal is when it is acting away from the center, correct? Which is the motion, which basically is the thrust that we are providing, the acceleration that we are providing while we are launching the satellite. So all these forces have to be balanced, and that's why Newton's first law basically governs this motion of a satellite. So this is a basic. Although I mean the things don't end here, because there are a lot of variables that we have here. For example, the Earth is not entirely spherical. That has to be counted. The orbits, most of the times, they are not completely circular. They are elliptical. That has to be counted. Then there is an air resistance that the Earth's atmosphere has. That has to be counted. The mass of the satellite itself, that also becomes a factor. That has to be counted. As the satellite goes up, the fuel is also reducing, meaning that the mass of the satellite is not even a constant. It keeps on varying, keeps on decreasing. That has to be counted. So there are a lot of variables that we have. We don't need to go there. That's why rocket science is called as rocket science for a reason, because these are concepts which are not supposed to be easy. These are difficult concepts, but don't worry about it. We just have to focus on the basics. There's this one question that was asked in your paper, a difficult question, a confusing question, but it was asked in your paper. So just go through the question once. Let's have a discussion on it, that what exactly the answer should be. I'm also launching a poll for you, so that you can take your time and mark your correct answer. Should we need to learn more about satellites, or what you teach is sufficient? What we are doing in the classroom will be more than enough for you in for the examination, so don't worry, don't go beyond that. Please explain the difference between meteorite and MTS. I don't know what is MTS. Can you please rephrase your question? All right, so a lot of you have the confusion where I thought you would have the confusion. So as I see, 8% of you have marked A, 12% of you have marked B, 38% C, and 42% D. So combined 80% of you have marked C or D, which is where a fair problem was supposed to happen. So let me read the question. The artificial satellite orbiting around the Earth does not fall down. This is so because attraction of the Earth. First is does not exist at such height. It's impossible. It's impossible that there is no attraction. I mean, there is the gravitational force, right? This is what we are balancing. There is a gravitational force. Even up to moon, you have a gravitational force. So something which is just at 500 kilometers, or even let's say 20, 30,000 kilometers, of course, it will feel a very strong gravitation from the Earth. So one is definitely wrong. A is definitely wrong. That is neutralized by the attraction of the moon. This also can't happen because first of all, moon has a very less mass, and moon's gravitational field is almost one sixth of the gravitational field of the Earth, and moon is very far away. So moon will have no role to play here, so that is also wrong. Now the problem starts. Provides necessary speed for the steady motion, provides the necessary acceleration for the motion. So it's between speed and acceleration. The correct answer will be D. The correct answer is D, provides the necessary acceleration. Why? Understand this. What do we do here? We try to balance the forces, right? We try to balance the forces. What is the formula for force? Simple formula for force. Yes, mass into acceleration. Correct. Force is equal to mass into acceleration. Mass is predetermined. We already know what the mass of the satellite is going to be. So mass is not the problem. What do we provide? The acceleration, right? We provide the necessary acceleration for the motion. It can't be speed. Why it can't also be the speed? Also understand this, that there is a circular motion happening here or an elliptical motion happening here. So it's not only about the speed but also providing the necessary direction. So if let's say instead of speed, if the question or let's say the option was saying velocity, then I would just leave the question and go to the next question, because otherwise it becomes too confusing if velocity was given as one of the options. What is the difference between speed and velocity? That speed has only magnitude and velocity has magnitude and direction, correct? So we have to we have to think of both magnitude of how much speed you are providing plus the direction in which you are pushing this satellite. So that's why it is more about the velocity than speed. So if let's say option C instead of speed was velocity, I wouldn't attempt this question. But because it is speed and acceleration, acceleration is much more appropriate as compared to speed. So that's why correct answer will be D. I'm not saying it's an easy question by any stretch of imagination. It's a difficult question. It is a very confusing question, but it was asked in your paper. Now coming to the understanding of the orbits. So what we know is fine that okay, this is an orbit and this is an orbit that we are creating for any satellite. And there is a basic science behind choosing that orbit, that we provide the necessary acceleration, we provide the necessary force to this uh, satellite so that it can reach its orbit. But how the orbits function is something that two scientists played a very, very important role in making us understand. So first was Kepler and then there was Newton. These two scientists played a very, very important role. First, what did Kepler do? Kepler had given three laws of planetary motion. All right. He had given three laws of planetary motion. What are these three laws of planetary motion? This basically we are talking about these three laws of how planets revolve around the sun. This was completely an observation based law. These were observation based laws. The observations were made by the mentor of Kepler. But Kepler, while reading through all the journals and all the notes that was made by his mentor, he realized that there was a pattern. And then he further went on to study all these patterns for the next 10 odd years. And then he came out with these three laws, that these are three laws of planetary motion. What do the laws say? First is all the planet move in elliptical orbits with sun situated at one of the foci of the ellipse. Second says planets sweep out equal areas in equal times. We'll discuss all that, don't worry. An orbital period squared is proportional to the size of semi-major axis cubed. So don't, I mean, looks technical, but it's not. I'll tell you what exactly it is. So these three laws were given by Kepler, but for Kepler, these laws were only applicable to all the planets that are revolving the sun. It was not going to be applicable, not supposed to be applicable anywhere else. All right, so he said that fine, these are three laws which are being obeyed by the planets while they revolve around the sun. But then came Newton, and Newton generalized this. Newton gave a universal law of gravitation. All right, a universal law of gravitation. And this universal law of gravitation talks about any two objects in the universe. So now what it says is that it's not only going to be applicable for the planets which are revolving around the sun, but any object that is orbiting around any other object in the entire universe. So when if there is a satellite being launched and the satellite is revolving around, let's say, the Earth, then in that case the satellite will also obey the same three laws that the planets are also obeying while they are revolving around the sun. So that's when now the game changes. All right, the game changes, and something that was only applicable for the planets revolving around the sun now is applicable to anything revolving around anything in the entire universe. So that is how we see that Newton was able to generalize these three laws with the help of law of universal gravitation, which applies to any two objects in the entire universe. So what are these laws? Just try to understand these three laws first. First law says that planets orbit in ellipses with sun at one focus. Ellipticals. So we are saying that it's an elliptical orbit, something like this. That let's say this is a typical ellipse. Now this ellipse has something called as major axis and minor axis. All right. So bigger axis is called as major axis and minor axis is the smaller axis. And there are points which are called as focus. So there are these 2 points which will be called as the focus. Now all these ellipses, they can come in various shapes and size. For example, ellipse can be like this also, and ellipse can be like this also. Even a circle, even a circle is an example of ellipse where as you basically when you start to compress it, what will happen, that this focus moves here and this focus moves here, and the focus becomes the center of the circle, and the axis that you had, the major and the minor axis, they become the diameter of the circle. So you can say that even circle is a special case of ellipse. But anyway, not going there, what we are saying simply is that planets revolve in elliptical orbits around the sun, with sun situated at one of the foci of the ellipse. All right. So this is the first law that he had given. The second law that was given by him was this, that planets sweep out equal areas in equal intervals of time. What it means is that if you look at this particular picture, you have a 10 days period here and you have a 10 days period here. All right, 10 days period in both the cases. Now in such a scenario, what the second law says is that if the time period is equal, then the areas will be equal. These are the areas, right? These are the areas. So in 10 days planets will sweep out equal areas in equal intervals of time. What it also means is, if you see this, what is happening in these 10 days, the planet has covered more distance, has it? Correct. And in these 10 days, the planet has covered a lot lesser distance. So, what it means is that when the planet is away from the sun, it travels slower. And when the planet is near the earth, sorry, near the sun, travels faster. This is what the second law says. Planets move faster when closer to the central object, move slower when farther away from the central object. Correct? So that's why when the planets are away, they move slow. When the planets are near, they would move fast. Same applies for again anything. That even if you have a satellite moving around or orbiting around the Earth, when it is near, it will be fast. When it is away, it will be slow. And we will look at the application of this law as well when we go to the relevant section. Third law. Third law says what? Orbital period square is proportional to the size of semi-major axis cubed. Looks technical, but it's very simple. It simply says that if, suppose that you have the sun like this, and you have one planet here, and you have one planet here. All right. So the planet that is nearer to the sun, it will take less time to complete one revolution, and the planet which is far away from the sun will take more time to complete one revolution. Goes without saying. You will think that okay, this is common sense. Why is it even a law? Because before him there was nobody who had proposed something like this. Now you know a lot of physics and you have studied a lot of things, that you would think that okay, this is common sense, that when you are covering smaller distance, you will cover that distance faster. When you're covering more distance, you will obviously cover that distance in a much more time. So, for example, the Earth completes one revolution in 365 days. Pluto completes one revolution in 238 years, right? 238 years. Pluto takes to complete one revolution. So, obviously, it is farther away, it takes more time. Earth is nearer, it takes less time. This is what third law is simple. All right. So, these three laws were given, and these three laws were given for all the planets revolving around the sun, but again, um, extended to anything where anything is revolving around something else. So this is how these three laws were proposed. If you have any doubts with regards to whatever we have discussed, please let me know. The basics of what we have discussed. Any question? Anyone? Is it open for all citizens? If you are talking about Hanle, then yes, it is. Just that while going there, you have to register. They would note down the time and the purpose of visit and all that. And while you are coming back, they will just see whether anyone who went has returned or not. But it's fine. I mean, every Indian citizen, of course, is allowed. Why does the planet, when revolving around the sun, does not collide onto the sun due to gravity? Simple. What we discussed, the first law applies here. Because the first law, it does not collide. Because what first law is doing is that it is balancing the force. That planet is at a spot where the force of pull of the gravitation is being countered with the motion of the planet around the sun. So that's why, just see this also, that how it also relates to the second and the third laws, that when there is any planet which is very near the sun, it is moving very fast, right? It is moving very fast, meaning exerting more force, because it is trying to counter more force of gravitation. Something which is far off is moving slower, because it does not have to exert as much force as the planet which is nearer the sun has to exert. So a very simple one line answer would be Newton's first law, where the forces are being balanced, one due to motion of the planet and second due to gravitation of the sun. Kepler law is applied for planets like Earth, right? Yes, completely correct. For all the planets, and then later Newton, when he came, he basically generalized it to anything in the entire universe. Please summarize all the three laws in one slide, please. All right, let me just take this. So, what we are saying is that first law says that all the orbits are elliptical. This is what the first law says, that all the orbits are elliptical and the sun is at one of the focus. All right, orbits are elliptical, sun at focus. Second law, it says that when planets are nearer, when planets are near the sun, they move fast. When planets are away from the sun, they move slow. This is the second law. And third law simply is that planets that are near take less time to complete one revolution or one orbit, whereas planets that are far take more time to complete one orbit. So this is, in simple terms, this is basically what we are saying in terms of the three laws. Why does the planets and other celestial bodies continue to move in space? Because the forces are balanced. As long as the forces are balanced, they would keep moving in the similar direction. What will happen at a certain point is that the sun is also continuously losing its mass. All right, we discussed that all the energy and the particles are pushed out of the sun, correct? So sun is continuously losing its particles. Losing particles also means decrease in mass. Decrease in mass would mean decrease in gravitation. When decrease in gravitation happens, this is where there will be a time when there will be an unbalance in the forces that will be created, and because of that unbalance in the forces, the planets will either fly off or they would simply crash onto the sun. But you don't have to worry, we'll not see that in our lifetime. It will take billions of years before that can happen. But until then, the planets will keep on continuing to revolve around the sun, right? So let's move forward. So based on our understanding, what we see is that there are three different types of orbits. There are multiple different types of orbits that you might have heard of: geosynchronous orbit, geostationary orbit, sun synchronous orbit, equatorial orbit, polar orbit. All these terms you might have heard. But essentially, all these different types of orbits, they can be classified into three types. What are these three types? Low Earth orbit, medium Earth orbit, and high Earth orbit. How do we define them? What is low Earth, medium Earth, and high Earth? High Earth orbit is any orbit that is beyond 35,786 kilometers from the surface of the Earth. That beyond the surface of the Earth, 35,786 kilometers, that is almost 36,000 kilometers. Medium Earth orbit is anything between 2,000 kilometers to 35,786 kilometers, and low Earth orbit is something between 180 kilometers going up to 2,000 kilometers. So the nearest one is the low Earth orbit, then after that medium Earth orbit, and then after that high Earth orbit. Now in this case, there might be a question in your mind: why this exact number, 35,786 kilometers? Why this exact number? Why not less? Why not more? Why not take a simple number, 40,000 kilometers or 30,000 kilometers? Why exactly this number? There is a very particular reason why this number. All right. Now, this number is mainly because when the distance is 35,786 kilometers, this is where the time period of revolution, the orbit period, basically the orbit period is equal to 24 hours. The orbit period is 24 hours, and that is the reason why this particular number. So there is no other reason that why this particular number. The number, because when you have any satellite which is placed at 35,786 kilometers, it will take exactly 1 day, exactly 24 hours to complete one revolution, right? So what is the significance of 24 hours? It's the rotation period of the earth. Earth completes 1 day in 24 hours. So when you have a satellite placed here, it will also take 24 hours to complete one revolution. So then what is the significance? The significance is because the earth is rotating in 24 hours, this point is revolving in 24 hours. What happens? This point becomes completely fixed, stationary with regards to this point, right? So that's why it will always remain permanently fixed, that if you are looking into the night sky, you might see that satellite as a fixed object in your night sky. So that is why 24 hours, because it remains fixed with regards to a point on the earth. Why do we keep it fixed? We'll discuss that, wait, but we'll discuss it. So these are the three types of orbits, and all these three types of orbits, they are based on distance. We'll further go into the detail of it, but before that, the three factors, there are three factors that determine any kind of orbit, and these three factors are taken on the basis of your requirements. So first is height. First factor is height. Now how is height a factor? Let me give you an example of it. All right, suppose that you have the earth like this. Suppose that this is the earth. Let's say there are these 2 points. A and B. Okay. Now, my question to you is, if let's say I had to take pictures of the earth, if I had to take pictures of the earth, should I launch the satellite to A or should I launch the satellite to B? I'm quickly launching a poll for you, not give you much time for it. But if I have to take pictures of the earth, whether I'll be at A or whether I'll be at B. A is of course nearer the earth, B is far away from the earth. So 41% of you feel that it should be at A and 59% of you feel that it should be at B. Okay, if an exercise. I just want to know that there what's the thought process when you think A or when you think B? Can you write in comments? Why did you answer as A or why did you answer as B? Or was it a lucky guess? Okay, so Dinesh, Binita, your answers are perfectly correct. Hmm. So there are two interesting points of view, and it's not that your points of views are wrong, but I'll still give you the answer why uh, one will be preferred over the other. So if I let's say I have a camera with me, suppose that I have to take a picture. All right. Let's say I have my phone, and from this phone I have to just take a picture. So if I had to take a picture from this phone, would I want to go close to the subject of what the photograph has to be about, or would I be far away? Would I want to increase the area, or would I want better clarity? Most of the times, I would want better clarity. Why? I'll tell you the answer. Suppose there is a satellite that we have launched, which is supposed to monitor disaster management. All right, which has been launched for disaster management. We are in the monsoons. There will be a lot of parts of the country which will be flooded, and flood relief has to be provided to these areas. Now, to provide better facilities, to provide better solutions and mitigation activities, you would want to take a very good high resolution picture. You would want to take very high resolution videos so that you can send it to the National Disaster Management Authority, and they can coordinate with the disaster management authorities and the local authorities to provide a clarity of what kind of steps have to be taken. If I compromise with that quality to increase the range, it will not help me. So that's why when we take pictures of the earth or videos of the earth, we always keep the satellite close to the earth. So range is not the problem for us, clarity is the requirement. So that's why we go after clarity and not the range. That many of you, as you basically had given the answer as B because you thought that a better range. You're not wrong in thinking that, but that's not my primary objective. My primary objective is to provide high resolution pictures and videos. So that's why whenever you have any satellite that is supposed to observe the earth, they will always be kept at A, not B. All right. So if I had to take a picture, I would want to be at A. When do I keep it at B? I would keep it at B when I need range. Where do I need range? Communication. So if I had a communication satellite, if I had a communication satellite, I will keep it at B. Because what happens is that let's say if this is the range of A, then this is the range of B. So B is having a better range. B will be my choice for communication purpose. Because if, let's say, instead of keeping the satellite at B, if I keep the satellite at A for communication, it's not that I can't, I can. But what will I do? I'll have to increase the number of these satellites so that I can keep covering all the parts of the earth. Not cost effective, right? Not cost effective. You will have to, I mean, instead of placing one satellite, you will place 10. Why would you want to do that? If you can do the same job with one satellite, that's better. So that is why range is more important for a communication satellite. Clarity is more important for an observation satellite. So that's why height matters, right? That's why height matters. So height will be taken into account while designing any orbit. Second is eccentricity. Eccentricity simply determines the shape of the orbit. Now, how shape is also important, we'll discuss that with example later. So you will get a better clarity when I go to that example. I'll come back and tell you why. Eccentricity basically determines how much elliptical the orbit is. So we'll discuss all that at a later stage. And then the third one is inclination. So inclination basically determines whether it's a polar orbit or an equatorial orbit. Whether it's a polar orbit or an equatorial orbit will be determined by the inclination. This also matters, and we'll discuss again with examples how it matters and where it matters. But these three become the primary factors. All right, these are the three primary factors that always have to be taken into account when we are talking about uh, an orbit, or when we are designing the orbit of any satellite. So that's why these three things become very, very crucial. If you have any questions, we'll take a small break here. All right, let's take a small break because too many concepts are running. So let's take a breather for like 10 minutes and let's be back. So it's 3:30 right now. So let's be back by 3:40 p.m., not more than 10 minutes. And then we shall discuss about the details of each and every orbit. But if you have any doubts with regards to what we just discussed about the orbits, these are artificial satellites. That's correct. Satellites can also be fixed or revolves around the Earth. They always revolve around the Earth. They are not fixed. Inclination means either it is polar inclination, inclined uh, with the poles, and either or it can be equatorial, meaning that it is in the line of equator, in the plane of equator. We'll discuss that later. Don't worry. Right, so let's take 10 minutes and we'll be back 3:40 and we shall continue with our discussion. Welcome back, everyone. So, we are talking about your orbits, and now we discussed that there are three basic types of orbits, right? One is low Earth orbit, one is medium Earth orbit, and then there is high Earth orbit. So, we'll try to understand what do we mean by these orbits and what are some of the characteristics of these orbits. How do we use these orbits? For what kind of applications do we use these kind of orbits? So first is low Earth orbit. So about what low Earth orbit, what we discussed is that this basically starts at 180 kilometers and goes up to 2000 kilometers. Correct. So this is what the low Earth orbit is. Now there are two types of low Earth orbits. One is called as polar orbit and the second one is called as sun synchronous orbit. Now, this sun synchronous orbit actually, in a manner, you can say that this is a special case. This is a special case of polar orbit. Right. So these would be called as special cases of polar orbits, sun synchronous orbits. Many a times when you look at the newspaper, when a new satellite is launched, you will see that they would use the term SSPO. So SSPO basically means sun synchronous polar orbit, because sun synchronous orbit is a special case of polar orbit. Now, why are we saying that it's a special case? And secondly, why the name sun synchronous? So first and foremost, these are polar orbits mainly because they are inclined towards the magnetic poles of the Earth. So we know that Earth has an inclined pole, and these are satellites which will be revolving in this polar orbit, and that's why they are called as polar satellites, or these are called as polar orbits. Now sun synchronous orbit is also a polar orbit, where we say that the sun synchronous orbits, they are synchronized with the movement of the sun. That's why they are called as sun synchronous orbit, or in other terms we say that these are synchronized with these are synchronized with the local solar time, the local solar time of a place. Local solar time of a place. What is local solar time? You know that the movement of sun every place will be different. For example, let's say India, we follow an Indian standard time, but it's not that the movement of the sun is the same. When you compare Arunachal Pradesh with Gujarat, it's not that the when the sun rises in Arunachal Pradesh, it is still night in Gujarat, correct? And by the time the sun rises in Gujarat, Arunachal Pradesh already has seen more than 1.5, 2 hours of sunlight. Correct. So that's why the local times are different. Although we follow standard time for the sake of simplicity for the entire Indian region. Correct. So that's why local solar time. So uh, these are orbits which are synchronized to the local solar time of a place, and hence they are called as sun synchronous orbits. So special case of polar orbit. That's why we are saying that it's a special case of polar orbit. So what happens is that they would keep on revolving in a manner that they are synchronized with the local solar time of a place. Now, when it comes to this low Earth orbit, what we see is that low Earth orbit will be often used for observations of the Earth. We discussed taking pictures and videos. You need to be near to the Earth, and that is why the low Earth orbit. So when we look at the applications of the polar orbit, you'll see that all these are the various applications, because these are all the applications for which you need to remain very near the Earth, and that's why all these are the applications of the low Earth orbit, because these are Earth observation, or these are also called as remote sensing. This is also called as remote sensing. All right, also called as remote sensing or Earth observation. So these are all the ways in which the Earth observation satellites will be used. Now, when we look at these Earth observation satellites, what we see is that there are multiple different satellites that have been launched over the years for Earth observation purposes. There have been Cartosat series satellites, Ocean Sat, Resource Sat, Resat, Mineral Sat. There are many such satellites that we have launched, and all these satellites, they help in launching. They help in Earth observation. So that's why these are also called as Indian remote sensing satellites. Indian remote Indian remote sensing. All right. Indian remote sensing satellites, IRS is the name of the project. Indian remote sensing satellites, and these are all the other different types of satellites that we have launched over the years for the sake of Earth observation. Then after that, we have the medium Earth orbits. Now, in case of medium Earth orbits, we see that again there are two types of orbits that we define here. First one is called as semi-synchronous orbits. Now, this semi-synchronous orbit has a time period of revolution of 12 hours. So it has an orbit of 12 hours, meaning that in 12 hours it completes one revolution. All right. In 12 hours it completes one revolution. Now, meaning that it can complete two orbits around the sun in one day. And this is an orbit which is placed at 20,200 kilometers. Now, again, 20,200 kilometers has been chosen on the basis of having that 12 hours of rotational period. And this is the orbit which is used by GPS. Heard of GPS? We use Google Maps and everything, where GPS is enabled in most of uh, for using most of these apps. So GPS satellites, they basically use this semi-synchronous orbit. Now, in the medium Earth orbit, so generally we see that medium Earth orbit is used largely for navigation, because GPS is also a navigation satellite, correct? And there are others also which use the same orbit for navigation purposes. Now, apart from semi-synchronous orbit, there is a very interesting orbit that we have, and this is called as Molniya orbit. Now, what is this Molniya orbit? Understand this. That first of all, this Molniya orbit, this was designed by Russia. Designed by Russia, or you can say back then it was USSR when it was designed. Now, this is a very particular orbit, and understand why it has been designed. That let's say if you have a normal orbit or a normal communication satellite here. So communication satellite is mainly, most of the times it will be always in the equatorial orbit. So from here on, it might have a range like this. All right, it might have a range like this. So what happens is that it becomes very difficult for such an orbit to cover the poles. Such an orbit is not able to cover the poles well. Now, Russia has a very large landmass in the polar area in the northern hemisphere. So Russia was not able to take the full advantage of the normal communication satellites which are placed in the equatorial orbit. So then Russia decided that these orbits are not very useful for us. So we'll design our own orbit, and this orbit was named as Molniya orbit. Now look at this Molniya orbit. This picture that you see is of Molniya orbit. What do you see? Highly inclined orbit. Correct? It's an highly inclined orbit. Now, because it's a highly inclined orbit, what happens? When the satellite in this orbit, when it is near the Earth, what will happen? It will move faster. When it is away from the Earth, it will move slower. Because of that, what happens? It spends a lot of time in the northern hemisphere, and as soon as it goes to the southern hemisphere, it very quickly covers the southern hemisphere. Because Russia has nothing to do with the southern hemisphere, they are designing this orbit so that they can provide the communication to Russia and its landmass. So, application of which law? Quickly. Application of which law? We discussed about three laws of Kepler. Which law are we applying here? Exactly, second law. Correct. So, why second law? Because in second law, we discussed that when the object is, when the planet is near the sun, it moves faster. When it is away from the sun, it moves slower, while covering equal areas in equal intervals of time. This is what the second law was. Exactly that is being used in this scenario. So here we see application of second law. Application of Kepler's second law. All right. So application of second law, because of which it is able to cover a lot more time in the northern hemisphere. Now, in this scenario, so it was designed by Russia for communication purposes. So these are communication satellites. These are meant for communication satellites. These are meant for communication satellites. Now, in this particular scenario, there was one very interesting development that happened, because remember that these were the times of Cold War, that there was a block of USA, there was a block of USSR, and there was a Cold War between the two. Now, as soon as USSR said that, okay, fine, we'll have this orbit, and this orbit will help us have better communication, US said that no, they're lying. They are creating this orbit so that they can launch spy satellites in this orbit, because this is a new orbit. We don't understand what kind of orbit it is. We don't understand what the motion of this orbit is like. So that's why USSR will launch its spy satellite and try to spy over Europe and US with the help of this Molniya satellite or Molniya orbit. So this was the US side of the story. But the official side of the story was that it is meant for communication satellites, because Russia can't use the normal communication satellites or the normal communication orbit. Whether the allegations of US were true or not, we'll never know, because that was the time of Cold War. I mean, forget about Cold War. Even today, nobody believes nobody. I mean, Russia wouldn't say believe anything said by the US. US would not believe anything said by Russia. That goes on. And this was the scenario. The scenario was much more heightened at the time of Cold War, and hence we can't say for sure whether US was correct or not. Whether, apart from some of these communication satellites, did Russia launch any spy satellites or not, nobody knows. So, but this is how we basically see that all these have been actually used in the past. Now, talking about navigation, because in the medium Earth orbit, most of the applications are related to navigation. Not always, although, for example, when it comes to India, in case of India, there are two navigation systems that we follow. One is the Gagan system, one is the Navik system. The Gagan system basically is a system which is using, just let me show you this picture. Gagan system is the system that uses a set of two satellite systems, the GPS satellites and the GSAT satellites. GSAT satellites are Indian satellites and GPS satellites are US based satellites. So it basically uses a set of these two satellites together. Now, when it comes to the Gagan satellite, what we see with Gagan satellite is that this was basically designed to help in civil aviation. The most important application of Gagan has been in civil aviation, that it will help in civil aviation and get civil aviation applications for India. Now, what happens in this particular scenario is that when we look at the Gagan system, when we look at the Gagan system, we say that this is GPS aided geo augmented navigation. That's why GAGAN, Gagan. So now, using GPS and GSAT satellites to provide accuracy to civil aviation, what exactly do we want? We want that we should be able to reduce the total flight path length of all the flights, all the domestic flights that are flying over the Indian subcontinent. By doing that, what do? We save, we shorten the distance. That's why we save some time, we save some fuel, and we save some cost. Environmentally speaking, lesser emissions as well. So it has all these advantages, and that's why, with primary purpose being this, we had actually designed the Gagan system. Although it does not only help in civil aviation, it also helps in other activities. For example, it does help in all these different application areas as well. So that's why Gagan, primarily ISRO and Airports Authority of India, they have designed it for civil aviation, but the applications go just beyond the civil aviation. Then, when it comes to the second system that we have in place, this is IRNSS, or Indian Regional Navigation Satellite System. Now, in this IRNSS, This, in a manner, you can say, is a system which is a replacement for GPS for us. Until now, most of the applications related to navigation we have been using GPS, but ultimately we want to get rid of GPS system. Why so? Because first of all, it belongs to US. So you can't have a control over the kind of data usage that they are doing. Even if they say that they are not using the data, can you really believe that the data is not being used? So in a manner, when we look at the perspective of security of the country, we think that it's always better to have a navigation system which is indigenous. And then there have been instances of the past, two specific instances, 1998 and 1999. 1998, we did a civil nuclear test, correct? We did a nuclear test and uh, not civil aviation, sorry, civil nuclear, a nuclear weapon test we had done. So now, in this case of nuclear test that we were doing, US somehow had some idea that we are working on some things related to we are going to test a nuclear bomb basically, and their intelligence was completely behind us. Their satellite systems, the same GPS systems, were constantly monitoring what is happening in India, so that they could see whether or not we are doing something like that. But very cleverly, we were able to bypass that. Then in 1999, so this was the first instance where US was keeping a very close watch on us with the help of its satellites. Then in 1999, in 1999, you all know that we were at war with Pakistan, and at the time of the Kargil war, we asked US for some information on the Kargil sector, because we wanted to fight back Pakistan, because Pakistan had captured some of the areas of India. So at that point of time, we went to US that we want certain data of these areas so that we can manage our movement accordingly. US refused. The GPS data that India asked for was not provided. Now, first and foremost, you are happy when you are spying on us. Secondly, when we need the data for very, very important uh, usages, you deny that data. This was, you can see, in a manner, an eye opener for us. We understood that we can't really wait like that. We can't really be relying on a foreign technology like this. We will have to build our own. And then you will see that 2 years later, 2001 was when a project was sanctioned. 2003, we started working on this project. By 2013, we completed this project. And then India has now its own navigation system as well. So now India, and it's not that India is the only country that has its own navigation system. Other parts of the world also, they have their own navigation system as well. So for example, there is GLONASS, there is Galileo. So every, I mean, many bigger countries, they have their own navigation system. uh, Bidu is there with China, so China has it, Japan has it, Russia has it, European Union has it, France has it separately, US, of course, Israel, India, all these countries, they have their own navigation system. All right, they have their own navigation system. So, and they all have been using all these navigation systems uh, for their own purpose. So now what happens is that we are one step closer. 2013 onwards, we started launching all these satellites, and we launched a set of 7 satellites, which are the IRNSS satellites for us. So in this manner, we already have the systems in place. We have seen that some of the companies, some of the mobile phone manufacturers, they already have started using the IRNSS systems instead of GPS systems in India. Xiaomi, for example, a Chinese company, they became the first company in India to start using the IRNSS systems instead of the GPS system. Many other companies also have started doing that. They have started using the IRNSS system. Two companies, the biggest phone manufacturers perhaps of the world, Apple and Samsung, these two also have been requested by the government that you also have to move, because these two companies have still not moved. They are still using the GPS system. So these two companies have also been advised that you also have to start making sure that you are using the Navig system and you're not using the GPS system. So that's why we see that all these are the things that we are doing. So set of seven satellites, but remember that these are satellites at almost 36,000 kilometers, 35,786 kilometers to be exact, and they cover not only India but up to 1500 kilometers beyond the Indian borders. And why beyond the Indian borders? Mainly because we wanted to cover the Indian Ocean region as well. So that's why up to 1500 kilometers beyond the Indian borders, the entire area will be covered by these systems. So when it comes to the IRNSS system, what we see is that this is an independent satellite-based navigation system to provide positioning, navigation, and timing services up to 1500 kilometers beyond the Indian borders. There are two kinds of services, one called as standard positioning service, and the other one is called as the restricted service. Standard positioning service is the service that every one of us can use. It will be the normal service that will be provided to everyone, but then there will be a restricted service, and restricted service is also called as precision positioning system. This is also called as precision positioning system. So this precision positioning system or the restricted service will be provided only to the people who are authorized to go to certain areas. For example, let's say the areas where our satellites are kept, the areas where the missiles are kept, any sensitive area of the country. So the government would not want that these sensitive areas, that strategic areas of the country, should also be freely accessible to everyone. So access to these kind of areas will be blocked, and the access will be given only to the people who are authorized to go to these areas. So that will be covered under restricted service. So that this also is a feature that helps us enhance the internal security matters of the country. So that's why from that perspective, having these services are very, very important. So this is basically what we see. The accuracy is supposed to be better than 20 meters. Recent reports also say that we'll have accuracy up to 10 meters, which is very, very good, meaning that if a point has been located, it is in the 10-meter radius of that point, which is a very good high accuracy to have. So in this manner, we see that all these have been the features of the IRNSS. Coming to the global positioning system, which is the GPS. Now, in case of GPS, what we see is that GPS is having a constellation of up to 34 satellites. Normally, although we see that there are 32 satellites which are operational, and it can be up to 34 satellites flying in the medium Earth orbit at approximately 20,200 kilometers. Now, in case of global positioning service or any navigation for that matter, there is a system called as triangulation. There is this system called as triangulation that is followed by GPS or even IRNSS for that matter. Now, understand what is triangulation. So, what happens is that let's say if there was only one satellite that was functioning and all the information was supposed to be provided by only that one satellite, then in that case, what happens is that the accuracy will be low. But what we do is why triangulation? Because we use three satellites. So one satellite, let's say, covers area like this. There is another one that covers the area like this. And then there's the third satellite which covers the area like this. So what happens is that when all the three are being used, they are able to provide a better accuracy for any kind of positioning service that you're using. So that's why triangulation. That's why triangulation, because we are using a set of three satellites for positioning and navigation. And this in turn helps us have a higher accuracy. All right, this helps us have a higher accuracy. So that's why we are using a set of three satellites in this particular scenario. So so that's why this particular concept becomes important from the perspective. Look at this question, a very simple question which was asked in your paper. read the question first, and then I'll launch the poll. Otherwise, the whole page, some parts of the page might be blocked by the poll. So just read the question, and then after that, I'll just take 30-40 seconds and I'll launch the poll. All right. So I hope you have read the question. I'm launching the poll for you. Please mark your answers. Hmm. So 36% of you have marked A, 52% B, 4% C, and 8% D. Okay. With reference to Indian Regional Navigation Satellite System, consider the following statements. First is IRNSS has three satellites in geostationary, which is correct. Three in geostationary and four in geosynchronous, which is correct. So first is correct. Second is covers entire area and about 5,500 square kilometers beyond Indian borders. What we discussed was 1,500 kilometers. 1,500 kilometers beyond the Indian borders. So that's why this is wrong. This is not correct. Because it's not 5,500 square kilometers. Let me go back. See here, 1,500 kilometers beyond the Indian borders. So that's why this is not correct. And then after that, India will have its own navigation satellite system with full global coverage by the middle of 2019. This makes no sense, right? Because first of all, we are not concerned about the full global coverage. All right, we are not concerned about the full global coverage. It is an Indian regional navigation satellite system. So that's why it is mainly about India. It is mainly about India and the Indian borders, and that's why this full global coverage is not really required. And anyway, middle of 2019 is not right. So that's why this is wrong. So answer should be one only. Now coming to high Earth orbit. Now before going to high Earth orbit, if you have any doubts with regards to whatever we have discussed until now, please let me know. Geosynchronous satellites. Okay, a couple of you have asked what is geosynchronous or orbit and what is the difference between geosynchronous and geostationary. We are just going to discuss that. So just wait for some time. Hmm. So some of you written in Google, it is telling IRNSS covers India and about 5,500 square kilometers beyond its borders. I don't think this is correct. I don't think this is correct because the information that I've taken from ISRO website, and ISRO's website says 1,500 kilometers only. So I'm not sure where you found this. India's satellite are over India only. Yes, I mean it does cover some areas beyond India as well. It does. It is going to provide some navigational information to countries like Nepal and Bangladesh as well. So, and Indian Ocean region is also being covered. So it's not typically only the Indian land boundary. IRNSS and GPS relation. There's no relation as such, but yes, both these satellites or both these satellite navigation systems, they are both uh, they're both navigational satellites. That's the only relation that you can think of. INSAT is also Indian satellites. Yes, it is. INSAT series satellites. We'll just discuss when you go to high Earth orbit. We'll have a discussion on INSAT series satellites as well. IRNSS was initially US based? No, no, not at all. IRNSS always has been Indian based and India only has developed it. So there is no way of US being involved here. Regarding the US GPS satellites are spread all over the world. Yes, they are. Basically, the GPS has divided the entire globe into six different regions, and there are a set of satellites for each and every one of those regions. So, yes, that's why it is a GPS or uh, global satellite service. Can we also use IRNSS in our phones for location purposes? You can't. The company has to take a decision. Depends on what phone you are using. Many of the companies they already are using the IRNSS satellites, and there are some companies which are still using GPS. Does any one of our satellites cover China? No, they don't cover China because uh, China would not allow us to use, and there are some international conventions that don't allow you unless you have a permission from that country to use that land boundary. All right, let's move on to high Earth orbit. So now, in case of high Earth orbit, first of all, we know that high Earth orbit goes beyond 35,786 kilometers, and we also discussed why 35,786 kilometers. So in this case, this is where the time period or the orbit period is of 24 hours, and that's why this particular height. Now what happens at this height is that this is the rotation period of the earth, correct? This is the rotation period of the earth. Now because of that, what happens is that if you have any satellite which is placed at this particular height, it also means that at this particular height they'll be able to cover this entire uh, they will be fixed with regards to a point on the earth. Why to keep it fixed? Because high earth orbit is where communication satellites are launched. High earth orbit is where the communication satellites are launched. Now the communication satellites, what happens is that the communication satellites, whether mobile phone communication, radio, television, anything that you're using, or any kind internet, anything, so any form of communication is using communication satellite. Communication satellites are at 35,786 kilometers. That's why remaining fixed with regards to a point on the earth. Why to keep it fixed? We want to keep it fixed because if let's say it was not fixed with regards to the rotation of the earth, then what happens? All the antennas and all the receivers that you have for catching the signals from these satellites, they will be confused. It will become very, very difficult for them to always set a connection with this particular satellite. So that's why they have to remain fixed. Just again, trying to simplify or oversimplify things, they'll be fixed, and that's why it's very easy connection between the earth and this satellite. Otherwise it will be very difficult if it is not synchronized. So that's why we have to synchronize, makes it easier. And that is the reason why this kind of an orbit will also be called as a geostationary Earth orbit, because it is stationary with regards to a point on the Earth, fixed with regards to a point on the Earth. So in case of geosynchronous and geostationary, again try to understand that in case of geostationary also, we say that it's a special case of geosynchronous orbit. So this will be called as geosynchronous orbit, and this is called as geostationary Earth orbit. So geosynchronous and geostationary. Now in case of geostationary and geosynchronous also, we are seeing the same thing. All right. So understand the basic differences on the basis of which we say that geostationary is different from geosynchronous satellites. How exactly are they different? We discussed about three factors. Remember that we discussed that three factors are there that determine any kind of an orbit. So the first factor that we had determined, we had discussed was height, correct? So on the basis of height, there is no difference. This also is at a height of 35,786 kilometers, and this also is at a height of 35,786 kilometers. This is the first factor. Second factor was eccentricity or shape. So shape wise, geosynchronous orbit can have an elliptical shape. All right, it can have an elliptical shape, but geostationary Earth orbit has a circular shape. Now, what is the difference between being elliptical and circular? When it is elliptical, there can be different types of ellipses, right? It can be elongated ellipse, it can be kind of a circular ellipse and all that. But there is only one kind of circle, correct? There's only one circle, and height is fixed, meaning that the radius is fixed. So radius is fixed and the shape is also fixed. Then comes the third factor. So first factor was height, second factor was shape, and the third factor is inclination. The third factor is inclination. So when it comes to inclination, this when it comes to the inclination, it has a small inclination with the equator. All right, small inclination with the equator. And in case of geostationary Earth orbit, it has a 0 degree inclination, meaning that it lies at the equator or in the plane of the equator. Now, because of this, what happens? See, in case of geosynchronous orbit, height is fixed, but shape is not fixed and inclination is not fixed. It can be 1 degree, 2 degree, 5 degrees, and so on. So then what happens is that you can create multiple such orbits. So that's why here multiple orbits are possible. Multiple orbits are possible. Whereas when it comes to geostationary orbit, it's a unique orbit. It's a unique orbit. There is only one such orbit. There is nothing else. There is just one such orbit. Why? Because height is fixed, shape is fixed, inclination is fixed. These are the three factors. We have fixed all the factors. So this is a unique orbit. So this is how these two are different. And that's why we say that geostationary orbit is a special case of geosynchronous orbit. All right. So that's why if you see geostationary orbit, it lies on the plane of the equator. It lies on the plane of the equator, whereas geosynchronous can have a small inclination from the equator. So this is how these two are different from one another, or not really different, but rather we'll say that geostationary is a special case of geosynchronous where you have fixed all these parameters or all these factors. Where will we use it? We will use it mainly for satellite communication. Any kind of communication, we will use these satellites. So telecommunication, telemedicine, teleeducation, television, mobile communication, radio, you can add internet to it. So all these will be used by these satellites. And there are two satellite services, one INSAT series and then GSAT series. Initially, when we started launching our satellites, it was INSAT series. But then when we were launching the INSAT series satellites, we did not have any launch vehicle that could launch these satellites. We did not have the capacity to launch these satellites on our own, because these are very bulky satellites. These are very heavy satellites, and that's why we did not have any launch vehicle that could launch very heavy communication satellites. So that is when it was INSAT. But then GSAT is when we developed our own capacity with GSLVs, and we started launching our own satellites as well. Then it became GSAT series satellites in communication. So these are the two families that have been used of satellites over the years. Look at this question. This was also asked in your paper. It's a simple question. All right. I'm launching the poll for you. Please mark your answers quickly. All right. So as I see, 56% of you have given A as the answer, 11% B, 28% C, and then 6% D. Okay. Satellites used for telecommunication relay are kept in geostationary orbit. A satellite is said to be such an orbit when the satellite is geosynchronous. It is geosynchronous. Why is it geosynchronous? What we did we discuss? That geostationary is a special case of geosynchronous. It's not different. It's a special case where you have fixed all the parameters, you have fixed all these factors, and hence it's a special case. So that's why it is a geosynchronous orbit. Essentially it is geosynchronous, which has all these fixed parameters. The orbit is circular. This is correct. The orbit lies in the plane of the Earth's equator. This is also correct. We discussed that it has 0 degrees inclination. So this is what we mean here. So that's why this is correct. Orbit is at an altitude of 22,236. I really did not expect anyone to mark this as an answer. In last 2-3 hours, I have taken this number 35,786 at least 10 times. After this, I don't expect that you would do this mistake. This is wrong, and you get your answer from here. Only from this one statement you get your answer. So this was simple. I don't know why so many of you marked 4 as correct. I have been saying 35,786, 35,786 so many times that even in your sleep you should get a dream of 35,786. So I don't know why this has been marked. Please be more attentive in the classroom. Please do that. So this is wrong, and answer will be 1, 2, and 3. All right. Moving on, there are other satellites as well. So what we discussed is that fine, there are all these orbits and there are all these satellites. That there are Earth observation satellites which are associated with the low Earth orbit. Then there are navigation satellites which are associated with medium Earth orbit and high Earth orbit, and then there are communication satellites associated with high Earth orbit. Then after that, there are satellites which are called as satellites for space science, where you have satellites like Astrosat, Mangalyaan, Chandrayaan, upcoming Gaganyaan mission, Aditya L1 mission. All these will be called as satellites for space science. Correct? So these are the examples here. Then after that, we also have some experimental satellites. Experimental satellites basically are those kinds of satellites that we would often use for carrying some kind of experiment. That, let's say we have to test out a component before an actual launch has to happen, a lot of testing also happens. That will be done with the help of experimental satellites. We have to do some kind of studies in the upper atmosphere, maybe something related to weather developments, maybe something related to climate change, and so on. So all these things can also be done with the help of experimental satellites. So here the example basically is INS. INS stands for ISRO Nano Satellite. ISRO nano satellite, and that's why these are also experimental satellites. Then after that, we also have small satellites. Now, when we say that there is something called as a small satellite, understand what a small satellite is. Any satellite which is less than 500 kg in mass will be called as a small satellite. And in this scenario also, there is a classification that we do on the basis of what is the mass. So for example, for any satellite that is between 100 to up to 500 kg, these small satellites, they are also called as mini satellites. These are called as mini satellites. Most of the ones that are between 25 kg to up to 100 kg, they would be called as micro satellites. Then normally in the range of 1 to 25 kg, the satellites that we have, they are also called as nano satellites. And then anything that is less than 1 kg, anything that is less than 1 kg is called as picosatellite. All right. So these are the four categories of small satellites. Now in this categorization that we have done, the most important category is this. Most important category is this, the category of nanosatellites. Now why exactly are nanosatellites important? What you would see is that of late a lot of satellites that are being launched, whether by India or even by many of the other countries, you'll see that they all have been launching satellites which are small satellites. Nanosatellites market has been developing, not only around the world or not only in the developed parts of the world, but even in the developing countries also. You will see that they are working on these kind of projects. For example, you take India. Last year we started with the launch of SSLV, a new satellite launch vehicle called as SSLV, that is small satellite launch vehicle. Small Small satellite launch vehicle. Now this specifically has been designed by India so that we can take care of all the smaller satellites that we want to launch. Not only that, it does not only help ISRO in launching the smaller satellites, but it also helps in launching many of the private satellites. So that's why we see that in all these cases, it becomes very, very crucial that India should have all the capabilities required so that we can launch these nanosatellites. So that's why we have seen all of a sudden nanosatellites uh, market has been growing, and very quickly we have seen that this market has been growing all across the world. So just understand, and let me just also note it down for you, the various advantages that we have for nanosatellites. Right? So nano satellites advantages. So first and foremost, where do we see the advantage? We see that they are cost effective. They are cost effective because does not take a lot of effort, does not take a lot of time in making these satellites. Not a lot of materials etc have to be used, so the cost is drastically lower compared to any big satellite that we launch or any big satellite that we develop. Then after that, the development is very quick. Quick development can be done. It takes, as we just discussed, takes very less time and effort, so that's why development can be very very quick. And then after that we see that when it comes to these kind of satellites, these satellites can also be launched very easily because these are 5 kg 10 kg satellites, so many a times they can also be launched with any other launch that we are doing. Many a times what you will see is that when India launches a satellite, there are a set of 8 to 10 satellites that we launch in a go. So at once we launch 8 to 10 satellites. Out of these 8 to 10 satellites, there would perhaps only be one satellite which is big, and all the other satellites are nano satellites. So you don't need special infrastructure to launch these nano satellites. You can basically club them with any other launch that you're doing and launch along with it. 2017, India launched a mission which is a world record, which holds a world record right now, PSLV C-37. In PSLV C-37, PSLV C-37, we launched 104 satellites in one single launch. 104 satellites, out of which 103 satellites were nano satellites. And there was only just one satellite which was a big satellite. It was a Cartosat series Earth observation satellite. So 103 satellites were nano satellites. Out of 104 satellites, there were only 3 Indian satellites and 101 satellites were foreign satellites. What were the advantages? First of all, we showed the capacity that we have the capability to launch these many satellites in just one single go. And secondly, also a mode of revenue generation for ISRO, because all these satellites which have been launched by India for other countries, they would also pay. There are other private companies, they would also pay. So it becomes a source of revenue generation as well. So that's why it becomes very very crucial in these kind of uh, areas where we see that we can do all this. So it becomes a source for revenue generation. Becomes a source of revenue generation. Then at the same time there are other things as well. For example, we see that it becomes easier for us to uh, launch constellation of satellites. That let's say instead of launching one satellite, we'll there was any project there is a project where you need 10 satellites to work. So nano satellites 10 nano satellites are easier, right? So that's why when we are working with constellation of satellites, when we are working with constellation of satellites, it becomes easier for us to use nano satellites there. So that also becomes one of the important changes. Then after that we see that a lot of experimental satellites can be nano satellites. Experiments, studies and research, there we can make the use of these kind of satellites. And then after that we see that they also can be used in a lot of ways. For example, they can be used in a lot of different projects when technology demonstration etc is being done. So in those kind of cases also we can make the use of these thing. And they also can be used in a lot of different ways. We see that there are multiple such applications that we have, and it helps India to also enter the private market, private space market. It also helps India to enter the private space market. And there are co-benefits that you have, that all these developments that are happening, they'll further help us improve in some of the other activities as well. So we'll see that whether it is about uh, creating better network, or whether it is about international collaborations, in all these cases also we'll see that nanosatellites will create a good market for India in all these cases. So that's why nanosatellites will have all these advantages. because and that's why we see that nano satellite market has also been growing. So this can be a question for you in the mains examination: the advantages, or what is nano satellite market, how is it changing the landscape of space technology. There are many ways in which they can ask you this question, but remember these basic points on how exactly to tackle all these different points. So that's why small satellites. Then after that, there are also some satellites which are university or academic institution satellites, where the satellite has been designed by the students and maybe the faculty of a certain university or the college, and they together would function to make this satellite, and ISRO would launch these satellites for them for free. ISRO does not charge anything. Of course, ISRO would not, because many of these students can't even imagine affording these kind of technologies or affording these kind of infrastructure. So this is a way in which ISRO also promotes among the students all these space activities. They can also generate a lot of interest among the students, so that maybe in the future these students will also come back and they would want to work for the space sector. Even if they don't work for ISRO, that's fine. Even if they contribute to the space sector in India, that will be a good growth. So that's why all these things will happen, and related to that only, we see that these kind of things, they also become a source for employment generation. And we see that a lot of startups etc also, they are also growing in this sector. So there are all, that's why all these advantages will happen, because ISRO is being more inclusive in all these kind of projects. So that's why these are the different types of satellites that we have. Look at this question. This question was asked uh, in your paper. Just read the question. It is somewhat a difficult question, but let's discuss this. I hope you have read the question. I'm giving you the option. So there is one change that you have to make. I think this one shifted here. This was supposed to be 3 only, and this is supposed to be 1, 2, and 3. I think the one shifted to 3. So 13% of you have marked A, 13% B, 29% C, and 46% D. The question says, for the measurement estimation of which of the following are satellite images or remote sensing data used? First is chlorophyll content in the vegetation of a specific location. So can we find uh, chlorophyll content in the vegetation of a specific location? The answer is actually yes, we can. What basically we have to do is we simply have to identify the intensity of green color. Intensity of green color, all right, intensity of green color. And if we are able to see what is the intensity of that green color, we'll know what is the amount of chlorophyll content in a given area. It also helps in a lot of ways. It helps us understand the kind of vegetation that grows in an area, and even agriculturally speaking, it helps grow take care of agriculture better, so that accordingly we can plan for that agriculture. So that's why one is correct. And that is the beauty of the high resolution cameras and the high resolution pictures that the satellites can take from low Earth orbit. Greenhouse gas emissions from rice paddies of a specific location. Even this can be done because we basically will be tracking how much heat is being released, what kind of gases are being released, and each and every gas has its own special marker, you can say. It has its own special marker, and you will be able to identify from that marker that what kind of gas. And especially when we talk about rice paddies, what gas is released by rice paddies? General, chalo, general knowledge question for you. Can you tell me the answer? What gas from rice paddies? Yes, methane, correct. Largely it is methane. So we can track methane with the help of satellites. So we can do that, all right? And then land surface temperatures of a specific location. Even this can be done because land surface temperature means what? Land surface temperature basically means infrared. So we have to track the infrared radiations. And if we can track the infrared radiations, we'll be able to track the land surface temperature also. So 1, 2, and 3. That's why the correct answer will be D. This question is a hidden question, a hidden current affairs question. All right. There was a satellite that was launched. The name of the satellite was HISIS. HISIS stands for hyperspectral imaging satellite. That's why HISIS. HYSIS. HISIS. So HISIS satellite was launched by India, and HISIS satellite would do hyperspectral imaging. Now this is where reading the current affairs carefully is important. Why I told you when we were discussing the strategy that you have to go into the basics or the static areas of current affairs as well. Now, when the hyperspectral imaging satellite was launched, the newspapers are reporting what? The newspapers are saying, "Okay, fine, it will have agricultural applications, it will have defense applications, and so on." But the very first thing as an aspirant that you have to think of is that if you're reading about hyperspectral imaging satellite, the first question in your mind should be, what is hyperspectral imaging? If we are releasing, or rather we are launching a hyperspectral imaging satellite, what is hyperspectral imaging? That's the first question that should come to your mind. Hyperspectral imaging is when you break down the entire electromagnetic spectrum, and for each and every smaller part of electromagnetic spectrum you do an imaging from that. For example, let's say we take pictures in the visible light, something that is called as a photograph, but x-rays can also do the imaging. Let's say if there is a fracture in the bone or we want to find something like that, we take the x-ray imaging as well. We can do the radio imaging as well. We discussed about the radio telescopes which take the pictures in the radio waves, right? We have night vision cameras which use infrared rays as well. So imaging can be done in any part of the electromagnetic spectrum. So when you are picking smaller units of these electromagnetic spectra and you are doing the imaging, it is called as hyperspectral imaging. And that's why with the help of hyperspectral imaging satellite, all these things can be done. So that's why this question was kind of a hidden current affairs question, that instead of listing this as HISIS satellite, they have reversed it, that what can be done with the help of satellite is the question that they had asked. So from that perspective, I wouldn't say that it was an easy question. I won't say that this is an easy question, but you have to try and infer like this. That is why I have kept this question here, so that you can understand the value of these kind of questions. Now there is one more orbit, and this orbit is called as Lagrange point. Last couple of years, Lagrange points have been in the news a lot, right? The last couple of years, we have seen that the Lagrange points have been in the news a lot. Now, how exactly they have been in the news? First, you know that we are about to launch the Aditya L1 mission, correct? So Aditya L1 is called as Aditya L1 because it is going to be kept at L1. L1 is this point that you see here in the picture. We'll discuss about that. Don't worry. So L1 has been in news because of that. Then, if you remember, last to last year, we launched James Webb Space Telescope. Now, this James Webb Space Telescope has been launched to L2, meaning this point. So that's why L2 has been in the news. Then we found certain asteroids which are called as Trojan asteroids. We found certain asteroids which are called as Trojan asteroids, and these were found at L4. There are two such asteroids. There is one which is called as 2010 TK7, and there is another one that is called as 2020 XL5. So these two Trojan asteroids have been found at L4. So because of that, L4 also has been in the news. So from there, we see that all these things make Lagrange points important. Although I've been saying this for the last 2 years, I was expecting that something will come, but still they haven't asked anything. Still remains important because Aditya L1 has not been launched yet. Has supposed to be launched this month itself, but we have to wait and watch, right? So not this month, maybe next month most probably. So because of this, all these Lagrange points, they have been in the news. Now what exactly do we mean by a Lagrange point? Try to understand this. If you see here, there are 5 points that we have here: L1, L2, L3, L4 and L5. All right, L1 and L2, if you see, this is the sun, of course, this is the earth, correct? So L1 is a point that lies directly on the line that joins the earth and the sun, and between the sun and the earth. L2 also lies on the same line but behind the earth. L3 also lies on the same line behind the sun. L4 lies 60 degrees ahead of the earth or ahead of this line, and L5 lies 60 degrees behind this line. All right. So in this manner, we have all these 5 points, and this is how we see these 5 points. Now, in this particular scenario, when we are looking at these 5 points, understand this, that why these points are special. These points, these are not imaginary points. All right. These are not imaginary points. These are real points which are produced because of gravitation, some kind of gravitational attraction or repulsion. So now what happens is that in case of Lagrange points, we say that these are positions in space where the gravitational forces of a two-body system like the sun and the earth produce enhanced regions of attraction and repulsion. So now the advantages, just try to think about the just try to think of the advantages that we have from this point. Why are we sending Aditya L1 to L1? What's the reason? Why? I mean, the entire name is Aditya L1. So why are we sending it to L1? L1 lies. Okay, first you answer. Just think of it. I'll anyway answer it. I just need a couple of answers from you first. Why do you think Aditya L1 is being launched to L1? Okay, close. Partially correct, Saurav. To study the sun's atmosphere in a better manner, Avni, you are also partially correct. Remote sensing of the sun, not entirely correct. To study sun's corona, yes, that's the application. But why L1? Why not any other point? Why L1? My question is why L1? To study the chromosphere in corona, that's correct. Yes, Himanshu, your answer is perfectly correct. To study the sun without being blocked by anything. So see what is happening here. L1 is a point which lies between the sun and the earth, and it always lies between the sun and the earth, always. So what happens is that, let's say the earth moves, right? Earth moves from here to here, correct? Earth moves from here to here. Now when the earth moves, suppose now earth is located here, then what happens? The straight line is here. So what happens? L1 now is here. L2 now is here. L4 would have moved to this point. L5 would have moved to this point. Right? So this is L5 now. This is L4 now. This is L2 and this is L1. And L3 would have moved here. So what happens? This entire system moves. So this L1 always has the direct access to the sun. L1 direct always will have an axis. Let's say it was a normal orbit. Suppose it was a normal low Earth orbit or a high Earth orbit. What happens then? It would keep on revolving around the Earth. So there will be times when it is facing the sun, and there will be times when it is behind the sun, behind the Earth, blocked by the Earth. So it will not be able to take a 24-hour observation of the sun. But when you have kept it at L1, L1 will always keep on facing the sun because L1 will have this orbit. Correct. L1 will have this orbit. So it will always keep on facing the sun. So that's why it is a beautiful point to keep any solar observatory satellite so that we can very easily see the sun from there. We can have a 24 access, full access to the sun. All right. So that's why L1. Now think why James Webb chose L2 as its point. Because L2 is behind the Earth. Behind the Earth means that it is always shielded from the radiations of the sun. So that's why L2, because we'll be able to shield it away from the sun, and it has very sensitive lenses and mirrors that have to be saved from the radiations of the sun, the magnetic particles, the charged particles coming from the sun, or even the X-rays and gamma rays which are coming from the sun. So we need to save the satellite, or we need to save the instruments which are there on James Webb Space Telescope. And also because it is in the shadow region, makes it easier to observe the night sky, makes it easier to observe the outer universe without being blocked by the harsh radiations of the sun. That's why L2. That's why we chose L2 for James Webb Space Telescope, and that's why we are choosing L1 for Aditya L1 mission. All right. So that's why understand why. Then L4 and L5. What we have found is that L4 and L5 is where L4 is where especially where you have these 2 points, these two Trojan asteroids. Now, first and foremost, what do we mean by a Trojan asteroid? A Trojan asteroid is a kind of asteroid which is also always associated with the orbit of a particular planet. It gets fixed with a particular orbit. That's why it is called as Trojan. So now what happens is that asteroids sometimes may get dislodged from their asteroid belt, and they might come across the Lagrange point of a planet, especially L4 or L5. L4 and L5, just remember that these are very stable points. All right. L4 and L5, they are very stable points. So that's why L4 and L5 is where when any, let's say, asteroid comes, the asteroid gets stuck there, and it will be stuck for a very long time. For example, let's say for these two asteroids, it is expected and it has been estimated that they'll remain here for almost 10,000 years. They'll remain here for almost 10,000 years, then only they'll be dislodged from L4 or L5. So this is how we see, and that's why Lagrange points have their importance. That's why L1 has its importance, or L2 has its importance. L3 is probably the only point which perhaps does not have that much importance for us, because L3 is where behind this giant sun that you have in the way, behind this you have L3. So establishing a communication from the Earth to L3, I would say, is impossible. Nearly impossible. Let's say nearly impossible, because you have this sun in the way. So that's why we can't establish any communication between L3 and the Earth. And that's why if you are an alien and if you want to park your alien ship, L3 is the point for you. L3 is the best point for you, because nobody from the Earth will be able to see what is going on L3. Park your spaceship at L3 and then launch an attack on the Earth from L3. But I hope that this lecture is not going to people like that. It's not even meant for aliens. So don't worry. So yeah. So that's why understand these Lagrange points. They constantly have been in the news from at least in the last 3 4 years. So that's why I still believe it will be an important topic, because questions still haven't been asked from here. Now, the last topic from this segment is GTO, or geosynchronous transfer orbit. Geosynchronous transfer orbit. So geosynchronous transfer orbit, just understand what we are using it for. Look at this particular picture. What you see here is that we are launching a satellite to 35,786 kilometers, which is the geosynchronous orbit or geostationary orbit also lies here. Any satellite that we are launching, the launch vehicles that we are using, whether we are using the PSLVs, whether we are using the GSLVs, all these launch vehicles, they do not have the capacity to go beyond 2000 kilometers and so on. They would be able to carry the satellite only up to approximately 2000, 2500 kilometers, not beyond that. So then what happens in such a scenario is that it becomes very difficult for, how do we take the satellite to 36,000 kilometers if the carrier cannot go beyond 2000 kilometers? This is where physics comes to the rescue, and we design a mechanism where from the low earth orbit we will be pushing the satellite to the high earth orbit. There will be an extra thrust that will be provided so that we can increase the path again, and there will be a new path that the satellite will start taking, and it will be pushed from the low to the high earth orbit. This kind of an orbit which pushes from low earth orbit to the high earth orbit is called as geosynchronous transfer orbit. So that's why the name geosynchronous transfer orbit, because you are transferring from the low earth orbit to geosynchronous orbit. So that's why the name has been given as geosynchronous transfer orbit. So we see that this kind of an orbit will be used when you are launching any satellite, like for example communication satellite, to the high earth orbit. So that is where we use this particular phenomena. All right. So this is the end of this part of our discussion. We'll move on to the last part of our discussion. We'll take a small break here, and after the break we'll be back with the next part where we'll discuss about ISRO, PSLVs, GSLVs, etc., and an introduction to the next chapter, that is energy, is what we'll do in the next segment. But meanwhile, if you have any questions, please let me know. I'll first take your questions, and then after that, let's take a break for now. Can eclipses also block satellites? Not really, because we'll be designing the paths accordingly. And anyway, eclipses are phenomena which are related to much larger bodies like Moon, Earth, and the Sun. Satellites will not really have a lot of effect there. PSLV and GSLV is the next section. So I will discuss everything about them when we go there. So please wait for now. PSLV is Polar Satellite Launch Vehicle. We are going to discuss about this in the next segment. So don't worry. Just wait. All right. So let's take a break here. I think the next session is scheduled for 5:30 if I'm not wrong. You might already know this. So we'll be back at 5:30 p.m. Let's take a break, go have some snacks, and be back with full concentration, and let's have a discussion further.